Alright, time for another DraftPhysics.com. DebatePhysics.com also, but the weasels really won't debate any of this stuff. So I have made extensive videos on the subject of light diffraction testing physics, the double slit experiment. So physicist Michael apparently hasn't any knowledge of that, you think a little bit of curiosity, he'd want to check that out. But anyway, regardless, he's made, this video showed up just now. So, after I already made my earlier video, because I definitely would have had fun with this. So anyway, we'll play this. It's going to be just so bad. It's just the standard crap, and it's all just that. Absolute crap.
Hey everyone. For this video, let's jump right into an experiment with light. Suppose we fire a laser at a barrier that has two slits that are very, very close together.
Right, so they're point sources, and we're going to put the point sources so close to each other they can't possibly create any interference. So the 2 points are so close that I can't draw a line from the two where I get a wavelength of difference. So it's actually a single slit experiment because I have annihilated these two surfaces. These surfaces, this one and this one and this one and this one, can't mean anything because they're so close together they're essentially a single point source. So that's the actual fact. He wants to make the slit so infinitesimally small that it's no longer a double slit. It's no longer a four surface experiment. It's just a two surface experiment, a two wave experiment, if you want to use that rhetoric. He's converted a double slit into a single slit, and he's going to get a single slit pattern.
We're going to fire the light through these two slits, and we want to know what's going to show up on a screen that we set behind these slits. So our diagram is going to look like this. We've got a laser, so we're going to be using an actual...
So again, it's just more bullshit graphics, the standard crap, blah, 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 blah.
laser over here. We fire that at an aperture that has those two slits in it. So the laser is going to hit that aperture, and some of that light is going to...
So his drawing isn't even right because this is essentially the single wire experiment, not the double slit experiment. He hasn't made infinitesimally small slits. He's made an infinitesimally small wire.
Go through, and we wanted to try to identify what is going to show up on the screen behind it. So you might want to spend a minute to think about what you think the outcome of...
So again, all of these videos are made to propagandize to children. So this is all bullshit for neophytes. So he's going to talk to ignorant people and try to convince them that this bullshit Huygens wavy crapola theory of Copenhagen and ESP particles and all this other crap is real, when no, if they actually did physics, if they actually analyzed the experiment, they could deduce that it's the surfaces that cause the effect. All of the fringe photons are photons that interacted with a surface.
This experiment is going to be, but let's kind of go through how we're actually going to do this experiment. So, as I said, I've got a laser over here. This is a helium neon laser. I'm going to be firing that laser at a barrier that I've set up. It's going to be exactly 2 meters away from this aperture that we're using. And the aperture that we're using is going to be...
is the standard crap that they make for these purposes, blah, 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 blah.
This plate. Now, this is probably going to be too hard to see on this video, so on the screen to the side, I'm going to take a picture of this plate and show that under D and E, there should be two, each one of those should have two very, very closely spaced slits.
So one of them is insanely, they're both very small openings, and one of them has a little tiny barrier to boot. So there's not even a big barrier between the two almost infinitesimally small slits. But the point is that this isn't how you make a double slit pattern.
Again, under both D and E. For D, they are really, really close together. For E, they're a little bit further apart, but each one of those only has 2 slits under each of those letters.
You could tell us how many nanometers of width the slits are, so we can compare it to the nanometers of the light.
So this is what we're going to fire the laser into. So that's going to be our aperture, and we're going to see what shows up on the screen. So I'm going to change the lighting in here so we can...
So now you can do the double slit experiment with very wide slits, and then you get real double slit patterns, very complex patterns, lots of stuff going on. And he's choosing to do it with a minimum amount of effect. For what reason? Oh, to propagandize. That's for what reason.
Actually see the laser beam a little bit more, get a second camera set up so we can see a better view than just this camera. So let's set up this experiment. Okay, so let's take a look at this experimental setup in a bit more detail.
Oh, I really don't want to do that. Maybe I'll speed that part up. I mean, who cares? So again, this is all just made to... I'm talking to an idiot. I'm going to explain what I'm doing to an idiot.
So I've got my second camera set up, so hopefully we can see this from 2 different angles. The laser is going to be aimed at the screen on the far side, so hopefully when I turn on the laser, hopefully this should be nicely centered. The center of that laser is right on the 50 centimeter mark, and notice that that screen is going to be exactly 2 meters away, from where I put this barrier. So we're going to use this barrier and see what happens when I shine the light through the 2 slits that are right under D. So let me write a couple of things on here. We're using D first. So we're using D, and the distance between those slits is 2 meters.
So why don't you write down the slit width? We like that number more than this rest of this crap, frankly.
So here we go. I'm going to put
the slit width, the distance really won't do anything. The distance just makes the pattern bigger or smaller. That's all it does. It doesn't do anything. The width of the slits are going to decide exactly how many bars there are and how big they are and where they are. It's all going to be decided by the distance between the surfaces.
this right here and make sure I line this up as nicely as possible and aim so it's going right under D. So hopefully that's clear that that's aimed at D. And let me move this camera, hopefully I don't run into anything. So you can see what's on the other screen. So all I've done is aim that laser through that spot D, through those 2 slits. And what do we end up getting over here? Well, we notice that we get this repeating...
Okay, so it is a double slit pattern. So the slits are wide enough, okay, that he hasn't annihilated them. So even though he said they're very, very narrow, they're not that narrow because there's quite a few bars here. So you got 1, 2, 3, 4, 5, 6, 7. Always an odd number. I wonder if he'll notice that. And these are, in this case, it's an odd number, but these go odd, even, odd, even. So, but that's basically saying, frankly, 7, you could figure this out on your own, but you could say, well, if this was 4, that would be 8. And so you can barely see the 4th dot, the one that's missing, frankly. The one that's not there. The one that's not visible enough because of the contrast. But you can sort of see it. There is a little vague spot right there. You can see that there is actually a dot there, because energy is actually going to that location, but it's just not from all 4 sources. All 4 sources are going to all these real dots, and only 2 sources are going to this dot. And that's why it's weaker. It's because only 2 sources are going there. So all of these little dots are actually evenly spaced, and they go around. They get bigger as they go around. So if you do this on a curved surface, as you should, because that would be equidistant, you'll get bigger and bigger. They get bigger and bigger as they go, and then smaller and smaller as they go to the top. And you can understand that this central maxima is really just 2 of these nodes merged into each other.
Pattern of bright and dark bands. So we get a bright spot right in the middle, and then as we go to either side, we get this repeating pattern of bright and dark bands. Now, notice that pattern continues quite a while. It becomes fainter and fainter.
So he hasn't talked anything about the ones that are missing, the missing bits. And why is the center maxima double? So they won't be able to explain either the double maxima or the missing bits.
But if I kind of block out some of the light from behind, I can even see a couple of dots. So they're really, really faint, but I do see
I don't know why he doesn't turn the light down, but whatever.
a couple of dots over here. So the result that we seem to get from this demonstration is that we get this repeating pattern of bright dots, not just 2 dots like we might expect from.
So it's obviously a repeated pattern that's interrupted. There's actually 2 patterns. There's an envelope pattern and there's the little dot pattern. So there's a big dot pattern with a double maxima, and then there's a little dot pattern with no maxima. And the little dot pattern has no maxima because the ones that are creating the little dots are the 2 furthest away surfaces. So the 2 surfaces furthest away from each other, those are the 2 surfaces creating the small dots. And the 2 surfaces closest to each other are the ones creating the big dots. And you can figure that out geometrically. You can understand that if I have 2 point sources further away from each other, there's a whole bunch of lines I could draw where there's a full wavelength of difference between the 2 lines. And if the closer and closer I make the 2 surfaces, the 2 sources, that there's fewer and fewer places that there can be a wavelength of difference. So it's really simple geometry. It's obvious the surfaces are creating the pattern.
From our intuition. And we want to know, well, why does this happen? You know, our intuition would probably say if there are 2 slits there, well, the light could go through one slit or the other slit, so we should get 2 dots on the far screen. But that doesn't happen. Our intuition doesn't work in this case.
So that's your intuition. It was never my intuition. I always knew the answer isn't that this is about photons interfering with each other, because frankly, photons don't interfere with each other.
Because our intuition is based on our prior experience, our everyday experience, and most of us probably don't have a lot of prior experience with firing lasers through 2 slits. So why does this happen? What was the cause of...
All right, so he's showing a pattern here, again, that isn't the actual pattern, right? So he's playing this video. He has a pattern on the screen. It doesn't match what's here as the animation. So, I mean, why is he doing that? I mean, why can't he recognize that there's missing spots here? That there's clear voids where there's not the supposed to be dot there that isn't there? Why isn't he emphasizing that as an important feature of this pattern? That maybe that a detective would look at it and say, well, that may be the cause. We can figure out, because of that, we can figure out what's going on. No, they don't do that. They just read out of their Bible.
Of this particular pattern? Well, in the last scientific critical thinking videos, I talked a little bit about falsifiability and different kinds of models. And if I were to say something like, oh, this was magic, well, not only can we not really test that, it doesn't give us anywhere to go. If I said that this pattern was produced by magic...
Well, your explanation is just as bad, so you don't have any explanation that isn't a mess. You have Copenhagen and many worlds and super universes, and string theory has some other explanation. I mean, you have all kinds of wacky notions. So what's the point of even talking about it? Because you don't even have a coherent theory to actually test.
Well, okay, what would happen if I changed some set? If I changed the laser light, if I changed something about the spacing of those slits? If I go with something, again, not really physical, I have no way of building a model from that has predictive power. So magic, even if it is magic...
just for the hell of it, I will, let's draw it just real quickly. I mean, I have done this so many times, so obviously, for a lot of people, this will be incredibly redundant. But just for the sake of just to clarify the simplicity of the argument, that what the real cause of this effect is, and it can be deduced so easily from the outcome, that all you're really doing is you're taking an opening that's made out of surfaces, and you could say you have 2 of these openings made out of surfaces, and they make a pattern on their own. So I could say here's a single slit pattern, and I could have an expectation that this is what I'm going to get, okay? Bars that diminish over time, but they actually still do the same thing, where they get actually bigger as you go down this slope. But that's what you're actually doing. You're just measuring 2 lines, and you're saying, look, how many wavelengths of difference are there in here? And you're just saying, well, that number of wavelength differences is really telling you exactly how many times you can have this line will be longer than that line. I mean, this line will be longer than this line. So it just tells you how many times that can happen. So the number of times your frequency of the light fits into this distance tells you exactly how many of these things there are. And if you know they have an average size, let's just say, obviously, like I said, as they go this way, they do get bigger and bigger, and they get smaller and smaller as they come towards the center. But the fact is, there's a certain number, and so this number, whatever this is, let's just say it comes into 10.5. All right. Well, if it's 0.5, I know that here has to be an off. Okay, because it's not a full wavelength, so it's out of phase. And that will tell me, frankly, what's going to be here. Okay. Because it has to be proportional. And this number, 10.5, will tell you exactly how many places there are in this 1/4 of the circle. It'll tell you exactly how many of these nodes there'll be. There'll be 10. There'll be 10 little dots, 10 places where you have an on. And there'll be 10 on this side. And it gives you the complete answer, and you can explain it all, and it's all quite understandable. And what you have here is an overlap. They can overlap a lot, or they can overlap a little, and it's the overlap that creates the central maxima. Alright, so I'm taking those two experiments and basically moving them into each other. So it's all about these surfaces. These are the point sources. In their own math, that's the distance, okay, that they're using to decide on, off. So it's exactly consistent with their own theory in the sense that the distance is the same. The point being made, though, is that these are actually point sources. These are actually new sources of photons. New photons are coming off of here as scatter. So pieces of a photon are being scattered by these two surfaces. And that scatter is arriving at the surface, and there's a 50-50 chance that they're going back in phase or out of phase, that the number's going to 10 or the number's going to 10.5. 50-50 chance which one you're closer to. And that's all that's dictating the creation of the pattern. So all of the fringe light, most of the light just goes straight through and hits the center and is very bright. Very, very, very bright. And only a small percentage of the light goes near the surfaces. The surfaces have electrons on them moving in and out. The electrons scatter the pieces of the photon. The scatter resolves your pattern. Okay, and the simple argument made for the double slit is I could have two of these same patterns, and if I put them 1 millimeter apart, you would see them right on top of each other. So they wouldn't make two separate dots, ever, because we're bringing them really close to each other, 1 millimeter of distance. And so at 1 millimeter of distance on the screen, right, because there's no reason for the photons to spread, there's every reason for them to go pretty straight. So I'm just going to have two patterns on top of each other. And I'm not going to have a dot here and a dot here, or a pattern here and a pattern here. All I'm going to have is a pattern, this pattern, right next to this pattern, and they're just going to be a millimeter off. So they're just going to overlap each other just a little bit. So that's another one of their canards, that they sell this idea that you should expect just two dots. No, I should expect two overlapping slit patterns. But the key feature is that when I do bring these two things in, I'm not going to overlap two patterns. I'm going to change the patterns fundamentally, because this is what I've done to the surfaces. I've created new point sources. The new point sources are this distance and this distance and this distance and this distance. So these aren't the only two distances anymore. When I bring these two together, all right, now the slit pattern is close to each other, and I got 4 point sources. You can see that it's not just these 2 point sources and these 2 point sources, it's this point source combining with this point source, and this point source combining with this point source. So it's two that are very close together and two that are very far apart, and that's what's deciding what's an on and an off. So that's why I get the more complex pattern where I have nodes in the middle, and then I have nodes on the fringe, and I have these dead spots where only 2 sources are hitting that. These 2 come up and hit there. The 2 outside surfaces are hitting there, but the 2 inside surfaces are 10.5ing. They're saying it's an off. So 2 are saying in phase, 2 sources are saying out of phase, therefore it's very dim. And that's all that's happening. That's the real double slit analysis. That's the facts. That's how it really works. And all of this mush they have created is just that mush.
That's doing this? That's not going to be a useful explanation. We can't solve a mystery by appealing to a bigger mystery. So, what might be a better way of approaching this? Let's say we consider a wave model of light. Instead of light acting like a stream of particles, we're going to think of light as acting like a wave and see if that gives us some...
A wave in what? Okay. So again, more mush. All right. So this isn't how it was done. All right. There were people who believed in waves, and they proposed this theory. And Thomas Young is the most famous one, and his diagram is essentially fake, because what he diagrams is two sources creating a single slit pattern. He doesn't diagram four sources, double slit. He diagrams a single slit, two sources. But he calls it the double slit experiment. But it's not a double slit because two of the sources are so close together, he's getting a single slit pattern.
Predictive power. So I'm going to try to model this with some material that I have here. So hopefully I can get this set up decently. There we go. And I'll also use this second camera to kind of show what I'm working on here. So let's say I'm treating light like a wave, and that wave has a bunch of wave crests. So this transparency, we're considering the wave properties of this to be the blue is where the wave crests would be, and the clear parts are where the values are going to be. Okay. So
you're just talking about lengths of lines, all right? So obviously the lengths of the line from one point to another. So all of these circles just represent the same length of line. And it's how many of those little circles are going to cross another circle will just decide whether you're crossing a 5 with a 7 or an 8 with a 10. Where they're in phase, but they're a different length of line. It's a different distance from one of the sources, and that's what constructive and destructive will end up being. But it really isn't anything destroying anything. Nothing is hitting anything. The radar experiment proves, the radio experiment proves this a bullshit. It's a falsifiable theory just by the fact that I can have two radio stations produce a signal, and I can move an antenna in between them. They're both at the same frequency, and I can move an antenna between them, and it'll go from in phase to out of phase to in phase to out of phase. I'll get signal, I get no signal, I get signal, I get no signal. It'll create the same pattern, and the two radio waves never interact with each other. They never interfere in space. So this isn't about interference.
This is giving off waves in all directions. Well, what if I took a second wave and had it interacting with this first wave? Okay. So now I've just got two waves that are...
So the four-source experiment, again, he's totally ignored his pattern, right? So he turned, again, he had a pattern that had the off spots. He didn't explain them at all, didn't talk about them at all, just completely ignored them. All right, so it's not about two sources, it's about four sources. The double slit is a four-source experiment, and the surfaces are the sources.
Interacting with each other. And we notice a couple of really interesting properties. One is that when I have these two waves interacting, there are going to be certain regions where those waves seem to be lining up with each other, and that is when...
Obviously no double maxima, so the first thing you can notice right away, there's no double maxima here. So we know that center he pointed at, look how big this grouping is, right? It's a big, big, big bright spot. No big bright spot here. So the fringe light, the light coming from the two sources, the surfaces, obviously aren't making this intensely bright. So in this case, if these were real waves, this wave would be just as dull as this wave, as dull as this wave. It almost looks like it's even smaller, frankly. But anyway. But this idea that it gets much wider as you go out is the part I wanted to emphasize. It's not as dramatic as this illustration he's doing, because this is only it's a very small number of nodes, as you can see. So it's only 1, 2, 3, 4, 5, 6. So there's only 6 units of distance between these two point sources, in the sense that the wavelength, the distance between these little lines, only 6 of them fit in this line here. So there's only 6 little nodes here. So 6 nodes here, 6 nodes here. All right, so that all matches. But you do see that these are much bigger, and that's just a consequence of the geometry.
We would get a very strong interaction. This is called constructive interference. If I have two waves and we get crests meeting crests and valleys meeting valleys, that's, for waves, it's kind of going to make super crests and super valleys. So along this direction, we get constructive interference, and that would show up as a bright dot.
So if it was water, it won't do that. It would just go up and down. The water goes up and down, and then it's calm, then it goes up and down. So it goes on and off. So again, the comparisons are so feeble. This is again comparing platypuses to ducks, and they're trying to prove they're the same animal. And they're not. Sound and water and whatever wavy stuff is not what light's doing. Light isn't a wave.
In other directions, we'd also get constructive interference. Wherever the crests of both of the waves match up and the valleys of both of the waves match up, we're going to get that kind of constructive interference, and those are going to be our bright dots. However, in other directions, along, say, this line, that is going to, right now we're getting the crests of one wave matching up with the valleys of the other wave. Okay? So along here, and here, and here, and here, things like that. Those.
It's just in phase, out of phase, in phase, out of phase. Wavelength of different, not a wavelength of different. I think comparing it this way is just going to confuse people, frankly. This is about a length of line. The line from the two sources at these different locations, the length of those lines is either one full wavelength different or not. That's the question. If it's not a full wavelength bigger or longer, then it's going to be destructive.
They're going to be dark sections. That's going to be destructive interference, and the light is going to kind of cancel out. So if light has these wave-like properties and the slit acts like two wave sources, we get this thing.
So again, it doesn't have wave-like properties except in a very superficial way, just like a platypus only has duck-like properties in a very superficial way. And it's easy to calculate and even to experimentally understand why it doesn't work. The radio signal proves this theory is nonsense. It proves that you don't need the two waves to hit each other. They don't have to interact at all, and you can create the pattern.
We call an interference pattern. It's sending out these two waves, and based on how those waves are interacting with each other, we are going to get these repeating patterns of bright spots when the waves are helping each other out, and dark spots where the waves are canceling each other out.
So here he has the classic shit drawing, all right? The double slit drawn as if it's a two-source experiment. It's not a two-source experiment, it's a four-source experiment. So again, he's just converting a double slit into a single slit. So he says, consider the light, and imagine the bigger paradox is when they have a single slit, they have to create two waves coming out of it. They can't have a pattern unless they can create two waves coming out of a single slit. Obviously, water doesn't do that. Sound doesn't do that. So it's just bullshit.
I also want to ask, so if we have these two close together wave sources, when those two waves interfere, we get this repeating pattern of bright spot, dark.
So again, wave sources. Did you hear what he said? He's describing a double slit as if it has two sources, when it clearly has four surfaces. And the two sources can only create a single slit, as he's displaying a single slit pattern. So he's talking as if he's analyzing a double slit. He's showing you a single slit pattern. This is how bogus it is.
Spot, bright spot, dark spot, bright spot, dark spot. Instead of just getting two waves showing up, we get this repeating pattern of bright and dark bands, which seems to match up fairly well with what we got when we actually looked at this laser. So it seems like this might be a plausible model, but in order for us to have confidence in this model, we must be able to make...
I mean, it's just so obviously missing the double maxima and the dead spots. So it's missing two fundamental features of the pattern. Two elemental features of the pattern are missing.
Testable predictions. In this particular model, if this wave interference is actually going the way that this model predicts, well, different points on the screen are going to be at different distances from each of the two slits. So when that laser light is going through each of those two slits, one of the slits is going to be a little bit further away from a particular part on the screen than the other slit. Well, if that is some integer number of wavelengths of the light, then we're going to have gone through one full wavelength, and if this is giving off a crest, this crest is going to match up with it, and those waves are going to be nicely aligned, and we're going to get constructive interference.
So the only way he can make this work for the laser pattern he has created is he has to take an average, and he has to pretend the dead spots aren't there. That's the only hope he has. So let's see what he does to try to do this single slit analysis using a double slit pattern. Let's see how he proves a double slit pattern with single slit analysis.
So based on this model, we're not going to go into the full math for this, but based
Okay, so what are we going to do? The half math?
on this model, if I have any integer m, we're going to get bright bands whenever the distance between the slits times the sine of the angle that
The distance between the slits, meaning what? The center impediments distance. So that's the two interior surfaces. So that's ignoring the outside dimensions, which are fundamental to the little dots. So he can't predict the little dots unless he pays attention to the outside slits. If you don't include the outside slit dimension, you have no hope of getting the little dots right. No hope at all. They're completely controlled by the farthest distance between two sources. Without that included, that is the source of the little dots, the outside surfaces. If you don't include that in your math, you're not going to get the right answer.
this light is being diffracted at is equal to some integer m times the wavelength of that light. But what other predictions does this make? So we're going to test out that one, but let's do a quicker prediction first. So right now, when these two wave sources are really close together, we get this repeating pattern of bright and dark bands. What happens to that pattern if I move the two sources further away from each other?
You're going to get smaller and smaller because you've got more wavelengths now in there, kind of obviously.
Well, if I move the two sources further away from
There
each
you
other,
go.
notice that that pattern of bright and dark bands gets a lot closer together. So if these two sources are really close together, that pattern of bright and dark bands should be more spread out. If those two sources
Spread out is the wrong word to use, but okay, fatter. The nodes should be bigger.
are further away from each other, that pattern of bright and dark bands should be closer together. This gives us a way of actually making a prediction for what should happen if I change this particular setup. If I change
So, you know, obviously that's not anything close to matching mathematically or coherently. Again, no central maxima here, and no missing nodes. So it's not a double slit pattern. It's a single slit pattern. It's a two-source pattern. A two-source pattern will look elementally and fundamentally different than a four-source pattern. So put two more of these diffraction gradients on here, or whatever they are, and you'll see a double slit pattern.
how far the slits are apart from each other. So let's give that one a try.
It's
So
going to be a little complicated just because it won't be able to turn it on and off where the two sources are, so you won't see the spots, the missing spots, because it will treat them as if it's the same as a four sources will look just like two sources. So frankly, it really wouldn't work.
let's set up this exact same experiment again. I still have the laser set up so that when I turn on that laser, the laser light is aimed right at the 50 centimeter mark. Let me move my camera just a little bit so you can see this just a little bit better. There we go. So the laser is still centered on the 50 centimeter mark, and this screen is still exactly 2 meters away. This barrier is still exactly 2 meters away from the screen. And let's measure some of the properties of this light that we see over here.
All right, so this ought to be kind of funny, right? Because he just illustrated something very simple, and this is the more complex pattern. So let's see what he's going to do to this. Again, his math has to have the distance from the two furthest surfaces to get these little nodes correct.
So right now we're using slit D, and on the manufacturer's label, for
Which aren't very useful, frankly.
D, the distance between those two slits is equal to 0.125 millimeters.
So 0.125 millimeters, which is 1,000 nanometers, I think. I'm not sure. So anyway, it's a very thin little line. So it's a very thin impediment. He hasn't given us the dimensions of the slits. He's given us the dimension of the impediment.
Okay, that's for when we're using slit D on that barrier that we have.
All right, so let me explain that, and then maybe we will save the second half for another time, but we'll see. Let's do this. All right. So the trick of the math, all right, is that they're going to try to use two numbers instead of four numbers. All right. So they're going to try to use one distance instead of two distances. So what they're basically going to do is take a crude average. So they're really going to cheat in a subtle way. So you're going to understand that if I have a very small barrier between two slits, and then I have the slits, and they're also very small. So I don't, there's no point in me trying to draw that. But I'll just take 4 lines. Yeah, I mean, there's not much, no other way to do it really. Okay, so these are surfaces. So these are walls here, and this is a block here. The thing is I can take this distance. Okay, so that's the distance he gave us, 0.01 whatever millimeters or something. And or I can take this center, right? Or I can take this distance. So we know that these distances aren't going to be too great, but we know this distance is 3 times this distance. So we know that the distance from the two outside surfaces, if the impediment is just as big as the slits, that this distance is going to be 3x this distance. But what you would use in your math, you could use some average. So you could use a 2 here and a 2 here. So instead of using this distance, you could extend the difference to be the center. Or you can get the real right answer by going with the outside. But just understand, the smallest distance is creating the envelope. The smallest distance between any two surfaces. So whether it's this surface and this surface, or this surface and this surface, whatever one the smallest, that's creating the envelope. And whatever the furthest distance is, which is always the outside, that's creating the little dots. So just understand the mathematical fudge. The wider I make the slits, the less they can cheat. Because you can sort of understand, so this is the impediment, you can kind of understand that these numbers get dramatically different. Okay, if I don't have very narrow slits, or I don't have an infinitesimally or a very narrow middle, then the differences become kind of obvious, very dramatic. All right. So we'll play a little bit more of it.
And now over here, we want to measure where are we getting some of these bright bands. Now, just for simplicity, I'm going to try to measure how far from the central fringe is the 10th bright band. So we're starting from here, we're going, would be the 0th band, n equals 0.
So he's going to pretend, okay, away the real pattern. But like you said, you can see this one's right there, right? So you can see that it's weaker, but it's there.
We've got 1, 2, 3, 4, 5, 6, 7, 8, that one's kind of hard to see, 9, and 10.
So he doesn't pay any attention to the fact that that's hard to see. And in most slit experiments, it's impossible sometimes to see those missing ones. Okay.
And that looks like it's just past 60 centimeters, so going from here to here.
So it might be the quality of the laser he's using, and that might be why you actually see these, is because it's a more narrow bandwidth of frequencies. So the frequencies are all very much the same frequency, and that's why you're actually seeing these, is because there's less noise because you're not using different frequencies of light.
That would be about probably about 10.1 centimeters to get to that band. So
the bands are getting bigger as they go across the face of the surface. So they aren't the same size. So again, this is more just, this is analyzing the experiment the wrong way.
Let's write that down. For the 10th band, so that would be n equals 10 for this, that 10th band was exactly 10.1 centimeters from the bright central fringe. Let's do the same kind of thing. We're going to do the same thing, but instead of using slit D, I'm going to change this to slit E. Now for slit E, we're going to do this.
So he's only taking one measurement, and that is where is the 10th node of the widest dimension. So those are being created by the farthest dimension between two surfaces. And so he's fudging it a little because he's going to try to average it out. He's going to probably multiply the slit times 2. The slit width, the impediment width, he's going to multiply it by 2. But it's still going to be short.
Same kind of thing. But for slit E, the manufacturer's label said the distance between those slits was actually a little bit larger, so 0.250 millimeters.
So now we're talking about the distance between the slits again. So he's not giving us the width of the slits. He's just giving us the width of the impediment.
And based on our previous observations, based on this model that we are trying to develop, this wave model of light, if those dots get further apart, those bright bands should get closer together. So when we look at the 10th band, it should be smaller than 10.1 centimeters. Well, let's replace it.
So obviously, yes, by making the impediment thicker and the slit size is the same, right? You've extended the distance between the outside surfaces. So the outside surfaces are now further apart, meaning the little nodes will be smaller. That's the right analysis. That's the correct way to understand what he's talking about. And what he's talking is wooey mush.
So I'm going to move this over, and instead of looking at D, we're going to look under slit E. Get that aimed properly. There we go. Okay, so I've got that aimed. Again, we are looking under slit E this time. We go over here. Well, notice that these dots are now much more closely packed together.
And notice also that there's obviously the darks are even darker, a little darker this time. But yes, and it'll be the same idea that if you actually count these nodes, there's going to be an odd number in the center, and that's going to be essentially twice the number, one short of being twice whatever the number of nodes are on the sides. So you multiply times 2, how many dots are here? 1, 2, 3, 4, 5, 6. And you just basically say 12, and then you say 13 or 11 is what you're going to get here in the middle.
So if I'm starting from that bright central fringe, this one here, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right around 5 centimeters, but I'm going to go even further just to make sure that we get better measurements. If I'm measuring larger things, it's going to be easier to measure. So that was 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, now 20 is right past the 60 centimeter mark. So now it looks like n equals...
So you almost can't see these, but it really is interesting with the higher quality laser. It's too bad he didn't darken the room, because this is a really nice that you can see the two source photons. You can actually see that they are actually going there.
20 gives us that maybe 60.1 or maybe 60.2 for that. It's a little bit difficult to measure exactly. Let's call that 60 point. So that would be from 50 to 60.2 centimeters. That would be 10.2 centimeters. So let's write that one down. So for E, for the n equals 20 line, that I'm going to call this distance x for both of these. That x distance was 10.2 centimeters.
So actually this seems a little bit off, right? Because we are saying these nodes do get a little bigger. So there should be some fudge there. I mean, in this small pattern, you're not going to see the huge difference that you're going to get, but I'm just saying they should be getting incrementally larger, the nodes, as you move sideways. And viewing on an infinite plane isn't really representing the pattern. It really should be viewed on a curved surface.
So notice that when I increased the distance between those two slits, that diffraction pattern got closer together. That matches with our prediction based on this model.
Oh, really? Silly. Right. Duh. But, but again, what did you really observe you did? What did you do when you expanded the center? You expanded the outside. And again, I'll keep just making the argument. The only way you're going to know what those little nodes are is to know the dimensions of the outside surfaces. The two outside surfaces are really controlling the experiment in a substantial way.
Of this wave model of light. When I have a slit separation that is larger, that diffraction pattern should get more closely packed together. But let's actually...
It's not getting closely packed together, it's getting more places where there is in phase and out of phase. You're increasing the number of places where it gets in phase and out of phase. You're not shrinking or expanding the pattern. You're increasing the number of locations where it's in phase and out of phase. So he's saying this so wrong.
Go through the numbers for this and see. So before we do that, I'm just going to do a quick side-by-side comparison. I'm going to move the camera over here, and I'll move this camera over here, and this way.
So this is very unqualitative, okay? It doesn't have any, this isn't real data in the sense that, it's such a superficial thing he's recognizing. But, and he's ignoring the really important factual feature, which is that these dots represent a location in space, and you're creating more locations in space. You're not shrinking the pattern, you're not expanding the pattern, you're actually changing the pattern.
So this was the case for E when the two slits were further apart, and this is the case for D when the two slits are closer together. So when the slits are closer together, that diffraction pattern is a little bit more spread out. When the slits
So again, it's not spread out. The pattern has more elements.
Are further apart, when the slits are further apart, well, that diffraction pattern is going to be closer together.
And it's not a diffraction pattern, whatever that is. You know, it's a scatter pattern, frankly.
Matches what the wave model of light would have predicted, but let's see if we can go into this in a little bit more specific.
So this has nothing to do with waves. It didn't prove waves. It's clearly not the same pattern created by these two waves. It's not the same pattern as created by these two waves. It's clearly not matching. It doesn't match water. It doesn't match. It doesn't match. Lots of evidence that it doesn't match. Lots of evidence that the heavy platypus is not the light duck. The platypus doesn't have hollow bones, and it doesn't have all these other things that the duck has.
Specific measured detail.
The platypus doesn't fly, for fuck's sake.
So again, let's see if we can specifically put this particular model to a more specific test by putting particular numbers in here. So in our first test, when we used...
So this ought to be interesting, because again, the key point will be the distance he's using, okay? And the fact is that just can't match with the wrong distance, so his numbers are going to be pretty far off.
The aperture for D. The manufacturer's label says, again, that for D...
I could just see it. I could see he doubled the distance. So I told you he'd have to double the distance. He doubled the distance. Let's go back that one frame. Yep, there it is. Alright, so this is the distance, 125 millimeters. D equals 250 millimeters. So he doubled the distance. The impediment's this big, he doubled it because he needs to get to that outside dimension. Okay, so instead of taking the actual outside distance, he's making it bigger, but it's still off. It's still not right. Still not enough.
The manufacturer's label says, again, that for D, there should be two slits, and the separation between the slits from center to center should be 0.125 millimeters. So 0.125 millimeters, so let's write...
0.125 would be 3, so, no, yeah, 2 point, yes, exactly. So he's going to double it.
Write that one down. So on this equation, little d would be 0.125 millimeters. And we need to be able to measure the diffraction angle. What was the angle at which that 10th band showed up? Because we were using m equals 10. And we need to figure out this angle this angle theta.
So this is all the angle math. It's just two lines. And all you have to do is draw the two lines from the two separate locations, and you can see if one line is longer than the other. So it's just it's so bogus.
So we can use some trigonometry because this is a right angle triangle, and we can say, well, the tangent of that angle should be the opposite side, the...
Right, we've seen all this so many times.
0.101 meters divided by the adjacent side, the 2 meters.
You could just measure the lines. So you could just say how far is it from this point to this point, and how far is it from that point to that point.
So if I rearrange this...
Just draw the triangle big enough, and you can just measure the lines with a ruler.
Do that division, so 0.101 divided by 2, and then take the inverse...
So divided by 2 is the same thing as making it twice as big.
...tangent of both sides. When I take the inverse tangent, I get my angle as being 2.89 degrees for that diffraction angle. And let's see if we can take this information together and figure out what is the wavelength of this particular laser, this helium neon laser. Okay. So we're saying that we should have d times the sine of that angle theta equals m times the wavelength. Well, that distance was 0.125 millimeters times the sine of 2.89 degrees equals 10, because that's which band we were looking at, times the wavelength of this light. Well, if I do 0.125 times the sine of 2.89, I get 0.00630 equals 10 times lambda. And if I divide both sides by 10, I get the wavelength of 0.000630 millimeters. Because right now this would still be in millimeters because we were using millimeters up here. Well, if I multiply that by 1,000, that would give me the wavelength in micrometers. And if I multiplied it by 1,000 again, that would give me the wavelength in nanometers.
There we
so
go.
If I take this and multiply by 1,000,000, that will give me 630 nanometers for the wavelength of this light. Again, this is a helium neon laser, and this kind of laser has a particular wavelength. So if we look up helium neon lasers, the best known and most widely used helium neon lasers operate at a wavelength of 632.8 nanometers.
Right. So there's no accounting for it, so fine. He got his answer. I'm saying it's the wrong distance, just factually. It's not the right distance. The outside surfaces are creating, okay, the distances of the little nodes. It's just a fact. And the inside dimension is the controlling the big giant pattern.
So the true wavelength, let me scroll back down. The true wavelength should be 632.8 nanometers. We got 630. I'd say that's a pretty close match on the manufacturer's measurement.
I guess I have to go through this again and figure out where he got this 2.89 degrees. It's 10 meters times 1.25. So it's the description on the card of this dimension. But it's still a small dimension. I mean, so it can't be the outside dimension. So I don't have an explanation for why it would be 10 centimeters for 10 nodes. So I haven't figured out first how he figured out 10 nodes should be in that 10 centimeters. So I guess I'd have to figure out how he did that. If it's wrong, I'm just, whatever.
Of what is the wavelength of a helium neon laser, and what we got by measuring this particular diffraction effect using this wave model of light. We get very, very accurate agreement between those two measurements. In fact, let's try the case for E. So for E, let's change this around. Well, again, on the manufacturer's label, the spacing between those slits should be 0.25 millimeters. Let me bring that up again just so we can verify that. So for pattern E, 2 slits, separation distance of 0.25 millimeters. Okay. So that one is 0.25 millimeters. This case, we were looking at...
You know what? I don't think that is accurate, actually. When he showed it, right? I mean, 0.25 is pretty big. I mean, 1/4 of a millimeter. 1/4 of a millimeter is really viewable. And, that stuff was really narrow. So I think those are the outside dimensions. I think he's giving you the wrong dimensions. He's giving you the dimensions of the outside surfaces.
N equals 20. And for measuring that angle, well, the screen was still 2 meters away. The distance along the screen, we said that was 10.2 centimeters, so point.
All right, let's see if we can go back to that slide. Apparently not.
Those should have 2 very, very...
All right, so we can't see the numbers in this picture. So, let's see with this, if I can find something on here that's a millimeter. So the card is probably 3 millimeters across. So a millimeter would be like this distance. So yeah, those numbers are the outside dimensions. I mean, a millimeter is, realistically, this card can't be more than 3 millimeters across. And maybe this little bar here I can see in the picture. Alright, so let's see if we have the picture of the card. Well, you couldn't see it when he holds it, so yeah, there's no way to see the numbers on the card to see if he's reading the right numbers. But I would argue that the numbers given are the actual numbers of the total width of the slit openings. The whole width is what the numbers he gave. The outside dimensions are the numbers he's using. Pretty sure. Alright, so let's just get through this math mush.
By the properties of those materials, it's an windows, and break it into its constituent wavelengths. So to finish this off, let's talk about some practical applications of this particular model, this wave model of light. We can use this.
So it's not a wave model, isn't really necessary. It's just a model indicating that you can break light into multiple sources and recreate the photons on a surface in different locations because the light was essentially bent. So you can bend the light by breaking it and then remaking it.
Diffraction effect to break up light by wavelength. This equation, if I have different wavelengths of light and the same diffraction gradient, they'll be dispersed by different amounts. So, for example, let's say I take my camera and I aim it through this diffraction grating. We can notice that it's able to take the white light coming through the windows and break it into its constituent wavelengths. This is the basis for spectroscopy.
Yes, and it's just moving the image, frankly. It's bending the image to a different location because each one of the little slits is breaking some photons and bending them to a location.
Basically a hugely applicable area of chemistry where we can identify chemicals by the different spectras that they're producing, identify the properties of those materials. It's an extremely useful application for talking about how light and matter will interact with each other. We can also use this to measure very, very small scale objects, down to molecular sizes for, in the case of X-ray crystallography. So let's look at this particularly with a CD and a DVD. And I'm going to take the laser and aim that laser. Let's start with the CD. So I'm going to aim the laser at the surface of the CD. And you can see that when I aim the laser at the surface of the CD, that light that's reflected off of there, it's being diffracted. We're getting all sorts of these patterns showing up.
Not all sorts. They're very specific distances between the nodes. So all of the little nodes have been made really weak. And the only ones where they're all in phase, so that is where each slit experiment, each little slit is sending light to the same location, that's where you have a bright, where they're all in phase. Where they're all not in phase, that is they're sending it a little bit out of phase, the length of their lines are a little bit longer or shorter, there's a bunch of little dots in between those main dots, but they're very weak because they're only coming from one source or two sources, where the big dots are coming from 50 or 100 or 200 or 5,000 sources.
And what's happening is the grooves in that CD, all the little grooves where the data is encoded, all of those are acting like those two slits and causing that light to diffract in different ways. The DVD does the same sort of thing, but let's look at its effect. If I look at the DVD, notice those dots are a lot further apart from each other.
So it takes a lot longer. There's so many more lines. So in this case, the more lines, the further the dots get, because it takes more sources for you to get the pattern doesn't repeat. So it's like there's a repeating pattern of cycles where they start to all go out of phase, and then they start to all go back in phase, and you get a dot. Then they go out of phase, and they start to go back in phase, and there's a dot. So you're just expanding the distance between the places where they're all in phase. So even though the DVD has more lines, more grading, the narrowness of the lines creates a bigger pattern in the sense of the distance between the pattern repeating is longer because there's more elements to the pattern repeating.
When I look at the CD, we get lots of dots pretty close together. When I look at the DVD, the dots are much further apart. I'm trying to see if I can get a dot showing up on the other side, but not showing up super well. There we go. Well, if I back up, we said that if that diffraction pattern is closer together, then the slit separation distance is larger. For the CD, that diffraction pattern is closer together. Those bright spots that are showing up, they're showing up closer together, which means the spacing of the slits on the CD is a lot further apart. There's less data that can fit onto a CD than you can fit onto a DVD. Because again, for the DVD, when I shine the light on here, that diffraction pattern is much, much more spread out. Can I get the one? Oh, got the other one just for a second. So there's one.
So it's pretty much what I said, but diffraction patterns are different. Diffraction gradients are functioning different because you always do have the fact that you have a bunch of the same size slits all next to each other.
On the other side, starting to show up, I have to kind of aim this properly in order to get that diffraction effect. But the basic idea here is I can measure very, very small scale distances using this diffraction effect. And if I use very, very short wavelength light, for example, X-ray light, I can measure distances down to the atomic scale. So if I want to measure the properties of a crystal, the different layers of atoms in that crystal will act like these slit separation distances. So this is where X-ray crystallography comes in. This also affects the maximum.
So there is some argument that could be made about whether or not it's as accurate as they're claiming it to be, because whether or not they're understanding where the sources are again. So we're talking about each line of crystal being a source, one source, not two sources.
Performance of optical devices like telescopes. So, for example, in pictures from the Hubble telescope or the James Webb telescope, when you sometimes see those spikes on objects, kind of a cross spike for Hubble images and kind of that 6 spike with the 2 extra little smaller spikes on the side, that has to do with how light is diffracting around.
Yeah, that has to do with the fact that the telescope has a surface, unfortunately. The light has to go through the opening.
Certain structures inside the telescope itself. We have to be able to take that into account if we're going to understand how these telescopes are making their observations. So again,
some of the light goes by the surface of the telescope, the interior surface, and it actually is bent, and it fucks your image.
There's a lot of applications for this, for looking at light as a wave phenomenon. It does get more complicated when we talk about quantum mechanics, where light comes in individual packets of energy, so we have individual photons of light, and this is going to get into the particle-wave duality of light, that it sometimes has properties like a particle and sometimes has properties like a wave.
And it really doesn't. It's always a piece of momentum, and that's all it is. It's a piece of momentum at a period. You get hit with little clumps at a period in time, and a package of those, ... ends up being enough energy to create an electrical impulse that you measure as a photon. We don't ever see photons. We see the effect they cause to matter. We see the electricity they create.
But that comes a little bit later when we have more data, because again, we are always going to learn more things when we have more good...
More data, completely wrongly interpreted, and in I think this case he actually has the wrong measurement. So he's actually got the outside dimensions of the slits, and he's posted that as the inside dimension.
Data, and we can always try to improve our models. So we'll call that good for today. Again, hope everyone's doing well, and if you have questions about this, these topics that we're going through, feel free to throw those into the comments below. I try to answer those as often as possible, or maybe another helpful person who's watching these might be able to answer some of your questions as well. And thank you as always for your attention, and
yeah, blah blah blah, preach the Jesus theory. God, praise God. Yeah, it's just so bad. It's just a religion. Alright, so this video will get posted as a response, and such, and so forth and whatnot. So, till the next time and such, blah 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 blah. This continues on and on and on. I mean, it's all hype. It's all just talk. I mean, again, Feynman couldn't even draw the pattern anywhere close to being accurate. I mean, it's just, they just don't care. They just want to sell this stupid theory. You know, in Feynman's case, his is the random theory, that every single photon just gets randomized by the random God. So the random God shoots the photon in a random direction. I mean, that's not a plausible theory. Anyway, till the next time and such.